This question asks you to evaluate statements about the least angle regression, LARS, algorithm, specifically the larspathgram function in scikit-learn. We'll examine each statement to see if it's a correct description of how the function works. This is the core topic. We are using LARS, a regression technique, but with a clever twist. Instead of working directly with the data matrix, X, we use its gram matrix, G, which is the matrix product of X transpose and X, XX, and a vector XY, XY. Using the gram matrix often makes computations faster. I'll break it down. X means the transpose of matrix XX as a vector resulting from multiplying the transpose of X with Y, the response variable vector. X is the gram matrix, G, representing the inner product of the data matrix with itself. These pre-calculated inputs make the LARS algorithm computationally efficient. After the computation, larspathgram gives us important things. Alphas are the values of the regularization parameter during each step of LARS, and cofs are the regression coefficients at each step. We also get additional information, but the alphas and cofs are the crucial outputs that tell us how well the model fits the data at each stage of the process. This statement is incorrect. I already mentioned that larspathgram works with the gram matrix, G, and the vector XY, XY, not the raw data matrix X. It doesn't need the original X matrix for its calculations. This is correct. Using the gram matrix is awesome. It avoids redundant calculations that would otherwise be needed when working directly with X, especially for high-dimensional datasets. This statement is entirely correct. The output, alphas, is exactly what it says. It's the sequence of regularization parameter values, L1 penalty, used in each step of the LARS algorithm. Absolutely right. By not requiring the repeated use of the large data matrix X in calculations, larspathgram is definitely a friend to your computer's memory, especially when dealing with gigantic datasets. This section introduces the multiple-choice questions about the larspathgram function in scikit-learn. I'm setting the stage for you to test your understanding. Here, I present you with 4 statements. I want you to identify the correct ones. This is where you apply what you know about larspathgram in the gram matrix. The ALPHAS output tells us the strength of the regularization at each step of the least angle regression. Think of it as a dial controlling how much we penalize complexity in our model. Each value in alphas represents a different setting of this dial. Using the gram matrix, G equals XX, where X is the transpose of X, cleverly avoids redundant calculations. Instead of working directly with the possibly huge dataset X, I pre-compute G. This significantly speeds up the least angle regression process, especially with massive datasets. Because I use the gram matrix, which is usually much smaller than the original data, I save significant memory. This is a huge advantage when dealing with datasets having many features. I'm asking you to determine which statements accurately describe the scikit-learn function. Lars_path_gram, which performs least angle regression, LARS. Remember, LARS is a regression method. The function larspathgram doesn't use the original data directly. Instead, I use a pre-computed gram matrix, G, which is X transpose multiplied by X, and a vector XY, X transpose multiplied by Y. This is key to understanding its efficiency. The larspathgram function is a specific implementation of the least angle regression algorithm within scikit-learn. It cleverly uses the gram matrix and XY to speed up calculations and reduce memory use. After running larspathgram, I get back some important information. ALPHAS gives me the series of regularization parameters used during the LARS process, telling me how much I'm penalizing complexity in my model. The COEFS provide the corresponding model coefficients for each step. I'm using scikit-learn, a popular Python library, to perform least angle regression, LARS. LARS is a special regression technique used to find the best model. I'm testing your understanding of the larspathgram function by asking you to evaluate some statements about it. I'm using a technique called least angle regression, or LARS for short, which is part of the Sklearn library in Python. LARS is a useful tool for figuring out which variables are most important in a dataset. It's like a detective trying to find the main clues in a case. To do LARS, I need two things: the gram matrix, G, which is X transpose multiplied by X, where X is the dataset, and XY, which is X transpose multiplied by Y, where Y is the output. Think of it like providing summaries instead of the whole dataset, saving me a ton of computation. The core of my work is this function, _lars_path_gram. It's a special function in Sklearn designed to efficiently perform LARS using the gram matrix, G, and XY instead of the raw dataset X. It's like a shortcut. After running _lars_path_gram, I get some important results. Alphas, which tells me the strength of regularization at each step, and cofs, which tells me the importance of each variable. Think of it as getting a summary report of my investigation. This statement is false. I don't need to use the raw data. The gram matrix and XY are sufficient. It is like using a summary instead of the entire book. This is true. Using the gram matrix is like using a map instead of walking every single street to get somewhere. It saves a huge amount of time, especially for massive datasets. Absolutely correct. The alphas values show me how much weight I'm placing on avoiding overly complex models at each step. It's like adjusting the focus of my detective work. That's correct. The clever use of the gram matrix helps me use less memory, which is a lifesaver when dealing with giant datasets. It's like having a small, efficient notebook instead of a huge, bulky file cabinet. I'm using the LARS algorithm, a statistical method from Sklearn, to perform regression. It's a fancy way to find the best fitting line, or hyperplane in multiple dimensions, for your data. Instead of using the raw data matrix X directly, I use a clever trick. The gram matrix, G equals X at X, which is the data matrix multiplied by its transpose. This gives me all the pairwise correlations in the data. I also use XY equals X at Y, which relates the data to the target variable. These pre-computed matrices make things much faster. This is the function I'm using from Sklearn to perform LARS. It's super efficient because it works directly with the gram matrix. The algorithm gives me two key outputs, ALPHAS, which are regularization parameters controlling the model complexity, and COEFS, which are the coefficients that determine the weights given to each feature in my model. The correct answers are B, C, and D. That's because using the gram matrix makes LARS faster and more memory efficient. B and D. Plus, the output ALPHAS really does represent the regularization parameters, C. Nope. I already told you that I use the gram matrix and XY instead of the raw data matrix. That's the key to the efficiency gains. Yep, that's a wrap. These are the correct options that explain how the gram matrix helps speed up the LARS algorithm while also explaining what ALPHAS represents. This represents the matrix product of the transpose of the data matrix, X, and the target variable vector, Y. I calculate this beforehand to speed up the least angle regression. Think of it as a pre-computed summary of my data's relationship with the target. These are the different values of the regularization parameter. Think of it like a knob controlling how much I'm penalizing complexity, that the LARS algorithm tries out at each step. The output gives you the sequence of these values, how this knob changed during the solution process. This is the Sklearn function that I use to perform least angle regression using the gram matrix. I'm using this special function because it's more efficient, especially for big datasets. This is my quiz question. I need to choose the correct statements describing how the function works and what it does. It's all about testing whether I understand the LARS algorithm and using a gram matrix. This is the core topic of my question. I'm using the least angle regression, LARS, algorithm, which is a way to find the best linear model. I use the gram matrix, XX, as a way to make the computations faster and more memory efficient. These are the things I feed into the lars_path_gram function to make it work. It's a bit like giving ingredients to a recipe. These are the results I get from the lars_path_gram function, like the final dish after following a recipe. I see lars_path_gram as the star of the show. It's a scikit-learn function that performs least angle regression, LARS. It's clever because it uses pre-computed information, the gram matrix and XY, instead of working directly with all the original data. This makes it faster and uses less memory. Think of it like this: instead of going through each ingredient individually to make a cake, you've pre-mixed some key components. This is a vector. I compute it by multiplying the transpose of the data matrix, X, by the response vector, Y. In simpler terms, I am calculating the weighted sum of each feature where the weights are the response values. It's a crucial pre-computation step for the lars_path_gram function. These are the regularization parameter values at each step of the LARS algorithm. Each value represents how much I penalize the complexity of my model. It's like tuning a knob to find the sweet spot between accuracy and simplicity. These are the model coefficients that LARS is estimating, at each value of alphas. That's the weight that each feature gets in the model. This is my output, after the algorithm has run. I'm asking you to pick the true statements about lars_path_gram, focusing on whether it uses raw data, its computational cost, output, alphas, and memory efficiency. This is the main topic. I'm using scikit-learn, a popular Python library, to perform a least angle regression. LARS is an algorithm that fits a linear model to my data, step by step, adding variables until it perfectly matches the observations. This statement is false. lars_path_gram does not use the raw data matrix directly. I use the pre-computed gram matrix and XY. This is true, because I avoid repeatedly handling the large raw data matrix. I am significantly more efficient. Absolutely true. I calculate XX and XY beforehand. This avoids expensive calculations during the main algorithm. That's correct. Alphas gives me a sequence of regularization parameters. This is the gram matrix. I obtain this by multiplying the transpose of the data matrix, X, by itself, X. It's a pre-computation that contains all the necessary pairwise inner products of the features in my data. Think of it as a summary of the relationships between my features. I use it instead of the entire raw data matrix because it is more compact and efficient for computations.